Vladimir Arnold, who is a famous mathematician, he once wrote that mathematics is the part of science where experiments are cheap.
Oh, I like that.
It seems as if there are a lot of places in the universe where our math simply just breaks down.
Is there a new kind of math that we're just waiting for you guys to invent that can help us out?
The math we have has become extremely good at explaining most of the universe. We have to abandon our notions of space and time. Even non-Euclidean geometry will not be enough to understand what quantum space-time looks like.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist, and we're going to have a Cosmic Queries edition on the subject of mathematics. Why would you laugh at me like that?
Apparently you're going to scare people with this? Everybody thinks there's a math quiz coming up.
That was a Halloween laugh, wasn't it?
It was.
I got Paul Mecurio here. How you doing, man?
I'm good, man. Good to see you.
Yeah,
again.
you got your podcast. What was it called again?
Inside Out with Paul Mecurio.
Inside Out. Did you get Disney permission for that?
I did not. Well, thanks for bringing that up. I'm going to be getting sued right after this.
And you are out of a job after May.
Yes, thanks for bringing that up as well. Anybody have any deadly diseases they want to talk about? Yes, the Late Show got canceled. So I work on the Late Show. You've been on the Late Show a bunch. We love you there.
Yeah.
Well, not everybody. No, and
you've been with
Stephen
with Stephen Colbert since the Colbert Report.
Since The Daily Show.
The Daily Show,
So,
yes.
I started at The Daily Show as one of the original writers, performers there. He came in as a performer.
Mm-hmm.
So
you predate him on The Daily Show.
I'm old school. I'm OG.
Wow. Okay.
And we actually shared an office together, would write a lot together. And then he had the Colbert Report. I worked on that. So he and I have been together a long time.
Okay.
Yeah. And it's weird and sad, because it's like, it's not a lot of changeover in the 10 years that we've been on the Late Show. So it's like a family breaking up. It's really kind of,
Okay.
So I'll be at your house cutting your lawn for $2.
Okay.
I hope our guest needs some help. I'll go to California. Doesn't snow out there, but I'll shovel anyway.
All right.
Yeah.
So,
and by the way,
Oh,
Baron.
you did get the title
You
of
knighted
Baron.
me Baron.
Only if the people asking questions remember that. That's where that comes from. You'll find out.
Right.
So who do we have today? I love me some mathematics.
Yeah, this
Ever
is
since high
fascinating.
school.
Brilliant.
I've been a big
guy.
fan of mathematics, even the obscure math that doesn't relate to anything ever, but it's still fun.
Yeah.
But of course,
Well, initially you like math because there's a finality to it, but then when you really get into it, you realize there's a whole bunch of non-finality to it. It can take you everywhere, right?
Yeah, everywhere and anywhere and everywhere.
Yes, exactly.
Yeah. So you know what we found? We found like a badass mathematician.
Ooh.
Yeah.
That sounds like a good movie title. Is he also an assassin?
We cannot divulge that publicly. We have Terence Tao. Terence, did I pronounce your name correctly?
That's correct. Yes, please be here.
Excellent.
That's wrong. That's not how you pronounce your name.
You are professor of mathematics at UCLA, UCLA. Okay.
That is not a community college in
UCLA.
Oxnard.
Yeah, UCLA Community College. You're professor of mathematics at UCLA. That's officially University of California, Los Angeles. Yes, it is. And here's the best part. Director of Special Projects at IPAM, Institute for Pure and Applied Mathematics.
Can I just ask, Terence, did they give you the title Director of Projects and you insisted the word special be put in there? That's what people are saying on social media. I'm just relaying information right now.
No, it predates me, but certainly that title helped me accept the position.
So we can say he has a special set of skills.
Oh, there you go. This guy is definitely badass.
He's got a special set of skills.
In a weird way, you could be like the accountant, right? That's that movie.
Yes.
Where he's mathematically brilliant, but then also could just kill you with 2 fingers.
Yes. But that is not our guest today.
Okay.
Enough with the superhero.
Right, okay.
So tell us about this center that you direct.
So I'm not the main director, but I'm the director of what's called special projects. Yeah. So IPAM is an institute that brings together pure mathematicians and applied mathematicians and scientists and people from industry to work on topics where it's time for mathematics to get involved. So, for example, we hold very early workshops and conferences on AI, deep fakes, self-driving cars, many years before they became a reality. And often industry people were working on these problems, but they were blocked by various mathematical obstacles, and they needed mathematicians to talk to. So we create these programs where we just have lots of experts in different fields in the same room, listening to talks and just socializing, and good things happen. I once talked with an electrical engineer and a statistician 20 years ago in one of these programs, and we ended up finding a new way to do MRI scans that's actually 10 times faster than traditional scans. In fact, now all the modern MRI machines use our algorithms.
Can I just say I recently had an MRI. Still took a long time. Maybe you could have done a little better.
Yeah.
Right. So
I mean, I don't have all day, Terence. I have stuff to do. I want in and I want out. I want it to be as fast as when I microwave soup.
Right. I think when they make them faster, they trade it off for more detail. So they can get a more detailed image of you. The cutting edge now is they can get videos of like your heart or whatever in real time. So since you're there anyway, I think they'll keep you for the same amount of time, but they can extract more data out of you.
At the risk of stating the obvious, one of the great things when you establish institutes or these umbrella gatherings of people from different professions that wouldn't otherwise ever talk to one another. I mean, think about it. You have departments of, mechanical engineering, electrical engineering, biology, chemistry, physics, and they have lunch together. They have coffee together, and they don't know what anybody else is thinking or what anybody else is doing. And now you put this umbrella over an institute, and you bring them all together, and oh my gosh.
And I would think one of the benefits is that you look at something yourself or with your group, a new set of eyes comes in and brings a different perspective and sees things that you didn't see.
Yeah, exactly. I mean, science is just way too broad now. Maybe 100 years ago, it was possible to have a pretty decent understanding of every corner of science, but that's basically impossible now. So you have to specialize.
The universe doesn't compartmentalize science.
As much as we wanted to.
Yeah, it's all mixed together at all times.
You guys figure this out.
Yeah, all the modern problems in the world are really interdisciplinary. I think the specialist problems we've kind of solved in the 20th century. And the 21st century is all about collaboration.
This should be obvious, but let's just so we're all on the same page. Tell us the difference between pure and applied math.
Pure math is curiosity-driven math. We see patterns in very abstract things like numbers or shapes, and we just ask, does this pattern keep continuing? It's not necessarily motivated by any practical application, or maybe it started out that way, but people just kept asking questions.
Would that include people who are obsessed with what's going on in the sequence of digits of pi?
In principle, yes, that is part of pure mathematics. It turns out not to lead very far because there basically aren't any interesting patterns there.
But did you prove that there are no interesting patterns?
This is actually still an open question.
So it could be that the fact that there's not an interesting pattern is itself an interesting fact.
Right, except that we know that like 99% of all the numbers in the world have no interesting patterns, and there's actually only a very small fraction of numbers that actually have something detectable going on. So the fact that pi is part of the 99% is, in retrospect, not exceptionally interesting.
Do we have a theory why 99% don't have a pattern?
It comes from a law of probability called the law of large numbers. Like if you pick a number randomly, just for every digit you roll a die, a 10-sided die, and you select digits at random. The law of large numbers says that 99% or 99.99% of the time, you never see any patterns. You get as many zeros as ones, as many ones as twos. There's only a very small fraction of numbers that exhibit bias. It's a very useful law. This is why, for example, we can do statistics polling. Like if you want to poll 300 million Americans and see what they're thinking, you can't poll 300 million Americans, but you can poll 1,000, 2,000. And the law of large numbers actually tells you that as long as you poll a very representative set of people, the outcome of that poll is actually pretty close 99% of the time to the general population.
So I could ask a question that you might be able to answer. How many digits of pi would I have to roll out before I got 10 nines in a row?
That would be about 10 to the 10. So I guess 10 billion.
Okay. All right. We got an answer to that.
You're both wrong. It's 11 billion. I'm the guy that knows nothing and you're both wrong. Why are we doing it now?
Okay. So now applied math, the world other than mathematicians care about the answer in applied math?
Right. Yeah. So applied math, it's still not quite directly applying to the real world. That's what scientists and engineers do. But it's about the mathematics that is of practical value to the to those scientists. So an atmospheric scientist might care about predicting climate or the weather, and applied mathematicians might develop the software or the equations to actually model the atmosphere or oceans. They may not actually work directly with real data. They may only work with sort of test data or something, and it still has a lot of theory to it. But it's sort of intermediate between the pure mathematicians and scientists and engineers.
We face that a lot in astrophysics, where you can generate data that you can then apply your ideas to see if that works, and then you check later to see if the data you generate matches what you actually end up observing. So just the methods, tools, and tactics.
So when does applied mathematics sort of do a cheat, if you will, right? Sort of simplify things intentionally, drawing on pure mathematics. And where's that line where it's too much of a cheat, or it's just enough of a cheat that it's still...
Do you mean approximation?
Yeah, well, the term is intentional simplified reality, right?
Yeah. So there's a spectrum. So the real world is messy, and if you try to incorporate every single aspect of it, it's just too much to model, and you can't see the forest for the trees. So mathematicians intentionally simplify reality. They work with what's called toy models. Physicists call them spherical cow type assumptions, where you want to model a cow. It's actually easier for the physics if the cow is a complete sphere and frictionless. That's not realistic, but it's a good starting point. And then over time, you decide to add some friction, add some legs to the cow. But you start with the easiest cases to get some an initial idea. I guess the difference between math and the other science and basically anything else is that we can change all our hypotheses and work with these toy cases. Like, if you want to build a bridge and you're an engineer, you can't just build a toy bridge over a creek first and then build your way up to a real bridge. If you're a heart surgeon, you can't do some experimental surgery on rats or something first and then, well, I guess in training maybe you do, but
mine has. That's why I have a bad ticker.
Okay, well, my condolences. But in most professions, you don't get to play your toy models because you're not allowed to fail. But in math failure is very, very cheap. You try a problem, you don't solve it, fine. You just toss the paper away and you try again. No one gets hurt, no one dies.
Yeah, the patient doesn't die. Yeah,
exactly.
Yeah, and let me add something, because you just blew by the spherical cow. It's worthy of another comment. Okay, so in physics, everything is about simplification, because often the details, while they may be interesting, don't actually influence the outcome in any important way. Okay, and if they do, you would have solved the case then to see how it influences the outcome. So here's the point. You're tasked with, I want to design a cow that can maximize milk production. Okay, so then you say, consider a spherical cow. Okay, so a sphere holds the maximum amount of milk for the area. Okay, the surface area.
Okay, where are the legs and where's the head?
So now, if you add legs and a head and a tail, and that reduces the number, but it means I have calculated the upper limit to how much milk the cow is going to make.
Because what is that sphere?
The sphere, exactly. So you can't come in later and say, here, have the cow produce 5 times
as
much.
Having those details of legs, tail, and head,
it subtracts from the total. Yes.
That's the detail that you said doesn't matter. Matters.
Well, what I'm saying is, it caps how much you can think about that problem. It keeps everybody in the same room.
Got it.
Yeah. It's not an unlimited place to guess outcomes.
Have you found that applied mathematics can change a settled pure math theory? Has that ever gone back and sort of...
Well, let's lead into that by asking, tell us about unsolved problems in mathematics. And when they're solved, who solves them? Is it the computer person? Is it the pure math person? Is it something else?
Matt Damon writing on a board when he's a janitor?
Exactly.
Come on.
Well, increasingly, there's a conversation going in all directions. So traditionally, pure mathematicians just experiment with patterns, and they based on analogies and intuition they build up, they propose that some phenomena that they see for one type of pattern also extends to some other setting. but sometimes it comes from the physical world. Physicists notice that something keeps happening. So, for example, there are these laws in physics that seem to be universal. That there are certain distributions, like the bell curve distribution is an example of a universal distribution. If you plot, say, the heights of people or the size of cows, if you wish.
Can I just tell you something right now? I want a milkshake in the worst way. I am so craving one. Anyway.
But lots of distributions in nature have the same shape. In this case, a bell curve. There's even a meme about it on the internet.
And we would, in physics, and I think in pure math, it's a Gaussian curve.
Yes, that's the name for it. Yes.
Named after Gauss, a brilliant mathematician, one of the most brilliant there ever was, I think.
Yeah, so mathematicians did actually find an explanation for why this curve appears all the time. It's something called the central limit theorem in probability. But there are some other distributions that physicists have discovered that we haven't yet fully explained why they show up so often. Like gaps between spectral lines, and it's more technical to explain. But yeah, there are laws that physicists and other scientists have found are universal, and mathematicians and they're a good source of conjectures for mathematicians to work out. Well, mathematicians are in some ways exploring other universes, but just very abstract numerical universes, not as interesting as the sci-fi alternate universes.
So I mean, to put this in sort of practical terms, pure math versus applied, it's like you're painting a room and you exactly calculate the number of gallons of paint. And then 2 days later, you've made 3 trips to Home Depot because you need 3 more gallons and you're going to have a nervous breakdown because you didn't. That's the applied part, right? Once you get into it, you sort of go, oh, wait a minute, I didn't factor this in. And that's sort of what happens with applied math. And it would then correct some of your pure math calculations, right? So it's sort of this symbiotic relationship between the two. Right?
Yeah, so Vladimir Arnold, who is a famous mathematician, he once wrote that mathematics is the part of science where experiments are cheap.
Oh, I like that.
Before you invest billions of dollars in a new telescope or a collider or something, you do the math and you see what is theoretically possible, maybe assuming spherical cows and things. But it tells you in theory what you can and what can't do, and it sets good targets, and then it allows you to allocate the more expensive resources more intelligently.
T-Mobile 5G home internet has some big news you should know about. They now have the fastest 5G home internet according to the experts at Ookla Speed Test. Now, in practical terms, it means photo backups happen faster, streaming a documentary doesn't stall halfway through, the physics of waiting reduced. What's also notable is that this jump in speed doesn't come with added complexity. Setup is simple. You plug it in and you're online in less than 15 minutes. And the value side of the equation holds up too, with a plan price that's backed by a 5-year price guarantee. So if you want the fastest 5G home internet with a simple setup and savings that stick, get T-Mobile 5G home internet. Just visit t-mobile.com/home internet to check availability today. Price guarantee, exclusions like taxes and fees apply. Fastest based on Ookla Speed Test intelligence data, second half 2025. All rights reserved.
So I got here something called the Collatz Conjecture. What is that?
So this is a dangerous conjecture. It has trapped many mathematicians and amateurs because it feels like something so simple that we should be able to solve it. But it's been around for at least 100 years, and we haven't solved it.
Well, maybe if you tried a little harder.
We've tried. I've worked on this too.
If you were just a little smarter.
Instead of playing with spherical cows all day.
I could describe it. I'm just worried. As I said, it could trap some audience members to work on it obsessively. People.
That's good. We like trapping our people. So tell me about it.
Okay.
So these are the best of the unsolved problems are the ones that can be described simply.
So the Collatz conjecture, it's also called the hailstone conjecture for a reason I'll explain later. So it says the following. So you give me a number, your favorite number, 37 or 69 or whatever. Okay. And then we do the following. So if your number is even, we divide by 2. We make it smaller. So 16 becomes 8. But if it's odd, you multiply by 3 and you add 1. So if you give me 5, I multiply by 5. It goes 15, add 1, gives 16. So odd numbers become bigger, even numbers become smaller. So now you just repeat this process. So 5 becomes 16, but then 16 becomes 8 because it's even. 8 becomes 4. 4 becomes 2. 2 becomes 1. 1 is odd. You multiply by 3 and add 1. It becomes 4 again. And you end up in a loop. 1, 4, 2, 1, 4, 2, 1.
It always takes you back down to there.
Well, that's the conjecture. So we've used computers. If you take any number up to, say, 1 trillion, every single number that we've tested ends up going down to 142, 142, 142. But we don't know if all of them do. So it's called the Hailstone Conjecture because there's this oversimplified model of hailstones, again, a spherical cow type model of hailstones, where hail forms because a little ice crystal forms in the clouds. Sometimes currents bring it up where it's colder, and then more ice forms, and then it goes down a little bit, and maybe it melts. And the hailstone bounces up and down in the cloud, but eventually it lands to Earth. All the hailstones eventually hit the ground.
But just to be clear, they hit the ground because they reach a mass that the upward currents can no longer sustain them, and then they drop out.
Too heavy.
Yeah, and the bigger the hailstone, the bigger the uplifting air was that kept them there for that long.
And the bigger insurance claims for your car.
In principle, there could be some really unusually lucky hailstone that somehow always hit the currents that go up and don't hit the ones that go down, and just keep bouncing up and up forever. Occasionally you could sort of defy the statistical laws of physics. And so in principle, there could be this very lucky number that just sort of always keeps hitting the odd numbers and going up rather than hitting the even numbers to go down. It would be like someone who's consistently winning at a casino, at a game that's rigged. It's theoretically possible, but we don't know if you can actually do it with an actual number, and that's the Collatz Conjecture.
But this is so basic. It's sort of a yes/no moment, right? It's even odd. It should seem like, why does it devolve into chaos? Because it starts with such a basic premise. That's the part that's confounding me, and I guess obviously others. But
you are now confounded.
Thank you very much. Can I have my official spherical cow, please? Yeah, but what is that about?
So it's part of a general phenomenon called chaos. So you can have very simple operations like halving a number if it's even, or multiplying by 3 and adding 1 if it's odd. And as you say, if you just do it once or twice, it's a very easy operation. A kid in 3rd grade can implement it. But when you iterate even very simple operations over and over again, you can get vast amounts of complexity. And so sometimes you don't. Sometimes you get like these universal laws, like these bell curves, and things settle down. But sometimes you just get this enormous complexity. The act of reproduction and splitting DNA is fairly simple, but it leads to immense biodiversity.
We have computers. We have AI. Why hasn't the Collatz conjecture been affirmed?
Well, because we have to check an infinite number of cases.
We'll get to work on that.
I was going to say, there's a thing called a computer. Here, look at my finger. Just go like that.
Why don't we crowdsource it? All right, it's still not an infinite number of people, but there's quite a bit of computing power out there. The SETI Institute did it, where you would upload software and they'd give you data, and while your computer was you were not using your computer on screensaver, it was using your CPUs to calculate.
Yeah, so there was a project, I think it was called Collatz Grid, which was exactly that, like SETI at home, but for Collatz. And it did extend the numbers, so a couple quadrillion, I think, or 10 to the 18, 10 to the 19, we could do from this crowdsourcing. But no matter how much you do, there's still an infinite number of numbers left to go. So if you want to roll out all the numbers, you need proofs. You need You need to use mathematical laws that work for all numbers.
Otherwise, it's not elegant and it's not even interesting.
Well, it's not elegant. It's like you're putting a bunch of crazy ingredients in a blender. You always get, and it always outputs oatmeal, like every time.
Well, some problems you can only solve by brute force.
Are we any closer to solving this conjecture? I mean, how close?
So I worked on this a couple of years ago. I proved a result that if you take a really large number, like 10 to 15, 10 to 20, whatever, I could show statistically that 99% of all numbers that are very, very big would become very, very small, become much smaller than where they started. I couldn't show they hit 1, but I could show that 99% of all numbers become as small as, say, the logarithm of their number. So like 10 to the 20, I could show drops down to 20. 10 to the 100 drops down to 100.
You know what? I'm going to use a term from your world. Why don't you apply yourself more?
Yeah. So in mathematics, we very much value partial progress.
They're very good.
Yeah, we can't solve completely, but we are happy with half a loaf or 99% of a loaf because someone else can build upon that.
So do you like those math movies like the Beautiful Mind and the Matt Damon movie?
Good Will Hunting.
Good Will Hunting.
Do you sit there and yell at the screen, "That's not the way you do it"? Are you one of those guys?
I enjoy those movies mostly for the non-math part of it. Now, maybe if there's an expert in schizophrenia, they would be complaining at that, but saying that the math was very cool. I think this is common. I have a brother who is who did some CGI back in the day, and like every time it's an animated movie, he cannot enjoy the special effects because he knows how they were made. So I remember watching one of these movies. It's a movie called Gifted. Stars Chris Evans and this amazing young child actor who is supposed to be this math genius, and her mother was a math genius, and she was working on an unsolved math problem, and it actually was a problem that I worked on. And at some point, they were going to review some of her notes on how she was making progress towards the problem, and I was actually quite interested to see what they would do. And they actually showed a little snippet of her notebook, and it was actually some equations from one of my papers.
Wow!
Okay. 2 years before the movie was made, I actually got an email from a director saying we're making a movie about a gifted kid in math. Could you supply some samples of some math computations that would be look good? And I actually supplied some from my own work, some from others, and they said thank you very much. And I didn't hear from them for 2 years, and then this movie came out. So I was caught unawares, but it did actually come from me.
So before we go to our question base, there's one more. Just tell me about the Erdos problems.
Right. So Paul Erdos was this Hungarian mathematician. He was rather extreme. So mathematicians have a reputation for being a little idiosyncratic, but he was rather extreme even among mathematicians. He didn't own a home. He would travel the world constantly and crash on other mathematicians' couches basically for his whole life. But while doing so, he would talk math with them, and they would often write papers. He has like 2,000 or 3,000 papers. He's one of the most prolific mathematicians in history. And he was famous for posing problems that he would attach little cash prizes to often. Like, here's a little problem I just came up with. You get $25 or something if you can solve this problem. And in fact, many of these problems did get solved, and Erdos would send them a check with that amount of money. But these checks were almost never cashed because they were more valuable framed on the wall as someone who had solved an Erdos problem.
I want to be that famous. I can pay people and they don't cash the check.
Well, maybe if Mr. Smarty Pants cashed the checks, he could buy himself a house and not have to sleep in other people's living room.
No.
That's all I'm saying.
There's a biography of Paul Erdos called "The Man Who Loved Only Numbers," and that is a pretty good description of it. I met him once, and he basically the entire conversation was about math. He was not one for small talk or anything.
From my notes here, we have problem 1026. Is that the correct way to say that? And was that an Erdos problem?
Right. So So recently, there's been a systematic effort to actually there's a website which has collected over 1,000 Erdos problems.
So this is just a number. This is a rank. It's 1,026. Right. That's all that is.
Yeah. So we just gave each Erdos problem a number. This is the ticket that this number got. This problem got 1,026. And there's been a systematic effort in recent years to solve these problems by any means possible. So some people use pen and paper. Some people use computers old school with lots of computations, and some people are using AI tools. There was a recent problem, 1026, that got solved by a combination of all of these. Lots of people threw out ideas. There was a discussion forum, and people used the latest AIs to gather some numerical evidence. I was involved a little bit.
And I can ask a question, and it's relevant and not off track. So when you're collaborating that extensively, who is curating all of that? Who is in charge of that? You need someone to sort of kind of manage that process, right?
So surprisingly, it's very decentralized. It's there was about 5-6 people involved, and there was just a chat room, and we just all spoke, we contributed ideas. It was a very respectful environment. If we had to write it, we haven't written a paper. The problem was solved. We haven't decided to actually formally make it official paper. If we did, then we'd have to organize it a bit better. But a lot of these crowdsourced solutions, they're just actually very spontaneous and very organic. I actually like this mode of collaboration than sort of a more directed top-down thing where there's some principal investigator that sort of assigns tasks. We can do that too, but sometimes we get it from the crowd, which is great.
Yeah, and the PI won't necessarily always be the cleverest person. Someone can come in from somewhere else and jump right in on it. I just want to show off a little bit of my childhood math wizardry.
Please.
So 1026, that number is divisible by both 3 and 9.
Okay.
Evenly divisible.
Leave it to you.
No, we just add up the digits, and what do you get?
Okay, you get 9.
9, so it's divisible by 9.
Wow, there you go.
And 9 itself is divisible by 3, so it's divided by 9. Did I get that right?
Yes, that is a classic test for divisibility by 5.
Exactly.
So, but a meaningful chunk of its value is forced to line up in some order, right? Isn't that what this problem says on some level?
Oh yeah, we didn't say what the problem was.
Okay, yeah. So you can play it. You can phrase it in terms of a game. Like suppose you have a pile of coins, like 100 coins, and you arrange them in stacks. Like maybe you put 30 coins here, and then 50 coins here, and then 20 coins here. So you arrange them in stacks, and some stacks are taller than others. And then I get to pick some of the stacks and claim those coins for myself. But I can only pick a sequence of stacks that's in increasing order or in decreasing order. I can't pick a sequence of stacks that goes up and down. So your aim is to lose as little money as possible. My aim is to get as much money from you as possible. So you want to arrange your stacks to sort of bounce up and down in such a way that it's hard for me to find a sequence of coins that go up or a sequence of coins that go down.
And it's no matter how scrambled the list is, you can pick this up decreasing and increasing order, no matter how scrambled it is, right?
Right. Yeah. So, like for example, if you're only allowed to divide your coins into 3 piles, I can always pick the 2 biggest ones because the 2 biggest ones will either be an increasing or decreasing sequence. So I can always grab at least 2/3 of your coins. But the more columns, the more stacks that you're allowed to make, the less and less I can win from you. And the question was exactly how much. What is the maximum loss you can have from this game? So what is the fair price to charge from me to play this game?
So it's like there's chaos in this order in this chaos, right? It's like a crazy group chat, but there's always one guy making sense a little bit.
Yeah. So it comes actually from this theorem of Erdos and another mathematician, Zakaresh, that given any sequence of numbers that goes up and down, you can find within it some sequence that goes up for a long time or some sequence that goes down for a long time. Yeah, there is order and chaos, actually. That's almost exactly how it's described.
That's beautiful. That's a beautiful concept.
Well, I have a beautiful mind.
We should make a movie with that title. So you got questions?
I have questions.
And
some great questions as always.
Patreon membership.
And they're always terrific. And I'm going to jump right in here. This is JKW. Greetings, Professor Tao and Dr. Tyson. James from Norfolk, England here. My question is rather simple. How often are discoveries made in pure mathematics which would appear to have no practical application all the time outside the realm of pure mathematics, but subsequently find very useful applications in other fields? What is one of the most surprising examples of this?
I love that.
Yeah, no, this happens all the time. Eugene Wigner, a physicist, once called this the unreasonable effectiveness of mathematics in the physical sciences. There are lots of concepts that mathematicians played with for their own sake, and only later often decades later, did scientists realize they were valuable for other things. The most famous example is that non-Euclidean geometries. There you go. People played with notions of curved space. Not because they thought that the actual world was not Euclidean, but
wait, back up for a sec. There used to be just regular Euclidean geometry, okay, right. Where everything is flat.
Boring.
That's where you have squares with 90-degree angles and triangles have that the angles add to 180. There's that, and that has direct applications. That geometry stands for Earth measurement.
Oh,
think about that. You're measuring surfaces and things. Yeah. All right. So now.
Yeah, so Euclidean geometry has all these amazing theorems, like the sum of the angles of a triangle is always 180 degrees. It's a classic theorem. But they were very, very hard to prove, very complicated to prove. mathematicians were trying for a long time to see if there was any simpler way to prove these theorems. Like if you take away some of the axioms of geometry, could you still prove these theorems are at right angles and whatever? And then, but by doing so, they discovered these non-Euclidean geometries, where you're on a sphere or some hyperboloid instead of flat space. And now the sum of angles of a triangle is not 180 degrees. The area of a circle is not pi r squared. And these are very weird geometries.
And parallel lines converge or diverge.
Right.
Either or, yeah.
Depending on the curvature of the space. Yeah, it's completely wacky stuff. And what were they thinking at the time? Were they thinking, oh, this is just pure math, no one will ever care, but I'm going to do it anyway?
I mean, it's really like you're discovering things that you don't think you'll ever use. It's like either you're a genius or super anal retentive. Right? It's like you keep throwing stuff in your garage for 40 years, then you clean it out, and you're like, that's why I kept that hat box. See, I knew, right? Isn't it like that on some level? Just say yes, Terence.
Well, fiction and art is like that too. You explore worlds that aren't real, and there's value to that. So yeah, so these were kind of geometries that they weren't real in some sense until Einstein, when he was developing general relativity, realized he needed a theory of curved space, and he asked a mathematician friend, I think Marcel Grossman, hey, do you know of any mathematics that deals with curved space? He said, oh yeah, there's this non-Euclidean geometry stuff. There's this really bright guy Riemann who developed this wonderful Riemannian geometry, and he took a look, and it was almost exactly what he needed, almost word for word the language he needed to express the theory of relativity.
So it's almost like when you're doing pure mathematics, somewhere in your gut there's an instinct that there's something this can be used for or will be used for, right? I would imagine.
But that's not what motivates. They're not motivated by that.
No, but I mean, once you get in it, you start to go, I know this doesn't apply now, but there's something, isn't it as intuitive at some point?
Yeah, so my theory is that both pure math and science are motivated by compressing the world around them. So they have all this data. In the case of pure mathematicians, it's mathematical data. In the case of scientists, it's physical data. And they want some nice theory or explanation to compress all that data into something that they can understand. And somehow, when you compress either theoretical data or experimental data, it often tends to compress to similar-looking theories, even if they come from completely different origins.
Next question.
Let's move on.
These are good. That's a good one.
Yeah,
thank you. That was from Norfolk, England.
England. This is actually from the Turkish Republic of North Cyprus.
Whoa.
Yeah.
Nice.
Greetings, Jem here from Turkish Republic of North Cyprus. I hope you're all having a great day. Here's my question. If due to some reason we were to adopt another base system instead of 10 and spent all these years doing math in that system instead of base 10, do you think there would be theories that we would fail to develop? Alternatively, do you think we would have maybe developed even better or more successful theories if humanity had been using another base number system all these years?
I love that. In fact, let's start out by asking you, when did the concept of base as a counting system reach maturity? That can't have been from ancient times, was it?
Well, I think like the Babylonians, every time you have to do either very big numbers or very small numbers, there's a limit to, you can give every single number a different name, but that really doesn't scale.
Yeah, every single numeral a different name. Right.
So the Babylonians had a base 60 system, for example. The reason why an hour has 60 minutes and a minute has 60 seconds comes from the Babylonians.
So you get to 60 and then you start counting again.
Right. So you're back at 0.
Yeah. So in base 10, when you run out of digits, you come back again and you start stapling the digits together to keep counting.
But why do you just say, Terry, that you either have to start with a big number or a small number? Can you elaborate on that a little bit?
The way base systems work is that if you have a really, really big number, you try to break it up into tens, or in the case of Babylonians, 60s. So, if you had 1,000 minutes, to describe 1,000 minutes, you break it up into hours, and it would be like 16 hours or something plus some change. So actually, humans have used multiple base systems. The Babylonians had base 60. Base 12, there's still remnants of base 12. We talk about dozens and gross, although gross is very archaic now. We use base 20, score, 4 score and 7 years ago. It's a base 20 system. The French still use base 20 in their number system. And computers use base 2. Binary, 0 and 1.
But does using one base or another hide certain access to discovery or reveal access to discovery? Because that's really what the question is getting at.
I think it can slow it down or speed it up a little bit, but you're still accessing the same numbers. So, it's always true that A plus B is B plus A, regardless of whether you use base 10 or base 20 or whatever. Once computers came along, people did experiment with, there was a base 3 system that the Soviets tried. It didn't work very well. We found that binary works really, really well for computers. And so, once we had to do computation at massive scale, we found the best base was base 2. But base 10 is completely fine for everyday purposes.
Nope, that's lame. Ready? Do you harbor questions about the universe? Some long-held bit of cosmic curiosity lingering within you? Or questions about anything at all? You can become a Patreon supporter of StarTalk. You have access to our exclusive question line on our website. Those are where we draw our questions for our cosmic queries.
Some of the most extreme objects in the universe.
StarTalk is a work in progress where we, every month, come up with some new way, some new idea, some new understanding of how to bring the universe down to Earth. We could not do that without your support. Thank you. And as always, keep looking up.
Hello, Dr. Tyson. This is Raul. Hello, Dr. Tyson, Professor Tao. I am Raul. I have a few stops on the C train from the Natural History Museum.
Oh, nice.
My question is to all of you, if you could, which means I'll handle this, guys. If you could, how would you change the pedagogical landscape for mathematics education? I recall reading an old math text where question at the end of the chapter had me write a short essay on the behavior of a function rather than do something more mechanical. This exercise was really quite beautiful and left me with far more intuition than if I had been asked to do something else.
Yeah, so what is the state of math education? Because there's this whole there's a whole demographic of the mathematically walking wounded. In their math class, they got bad grades, the teacher sucked, and now they have no appreciation for math the rest of their lives.
Right. It is a tough problem, especially since there's a shortage of really qualified math teachers. It's not a profession that is very appealing. Often they don't often get enough respect or salary for what they do. My theory is that different people have a different kind of math language. So some people are very visual learners, and they like to see lots of pictures. Some people are very narrative driven and they want to see a story. Some actually like working with symbols and solving puzzles. Some like playing games. Some like being competitive. So there's many different ways to access math. But when you teach a class of 30, 40 kids, you can only teach one way. And inevitably, many of the students in that class will not click with them, the style. So if there was some way to have multiple pathways to learn the same material, maybe outside the classroom, some enrichment activities, I think that would help.
Well, you can get into the mechanics of what you need to do to make it more interesting, but at the core of it, and I mean this seriously, and I've said this about Neil, it really is about the emotionality of the person delivering the information, right? If that person is engaged, I had a terrible science teacher in middle school. He smoked cigarettes and he'd be like, all right, we're going to make a battery today. And and I always say, if I had Neil as a science teacher, it's the only compliment I can give him, is I would probably be in science today because he emanates passion and enthusiasm and love and fun. And at that point, you can come up with all the sort of mechanical mechanisms through which you teach math. But if it's being delivered in a dry way by someone who's indifferent or disconnected, it is never going to land on the student.
You're saying mathematicians are generally unfun people.
They're all dead to me. I got to be honest with you. No, I don't mean that I mean about if any presentation to human beings comes through best when the person delivering the information,
whether or not it's math,
whether it's math, science, if you're talking about English, if you're watching somebody interview somebody on TV, you're only compelled in that interview because you're seeing a real relationship between two people, which emanates initially from the host. It's all about emotionality, and then the information comes and is absorbed.
Yeah. So if the teacher doesn't care, the students won't either. But good teachers are so precious and so rare, hard to find.
So are you a good teacher?
I try. Yeah.
Time for a couple more questions?
Sure, absolutely. This is William Warren. William from Abingdon, Maryland. Maryland. When you're working on a very difficult proof, how do you decide whether you're missing a key idea versus simply not pushing far enough with the tools you already have?
I love that.
Yeah.
Good. Yeah. Because in physics, when we approach a problem, you first lay down all the parameters. And if you're missing a parameter and don't know it, you're not solving the problem.
Right.
So if you're solving a problem that's never been solved before, how do you gain the confidence that you have everything necessary at your disposal to actually solve it?
So it's really important in math to not just prove positive results, but negative results. Results where you cannot prove the thing you want with the hypotheses you have, because you can find some counterexamples which satisfy all your hypotheses but don't satisfy your conclusion. Now, these hypotheses may not be correspond to the real world problem that you were working with, but by comparing that counterexample with the real world problem, you can see what you're missing. So actually, a lot of math is actually exploring the negative space of what doesn't work and what doesn't work. And it's only after you sort of map out all the negative space can you see kind of the very narrow path which dodges all the pitfalls and gets you to your goal.
Do you ever just say, I'm going to write it out cleaner and neater, and then the answer will appear? Do you ever just kind of clarify it a little bit?
So, sometimes, yeah, you can just what's the modern term, like raw dog it or something, yeah.
Raw dog. Oh,
yeah. That's what the young kids say. Okay, but
the youngins. But what you did describe was very Sherlock Holmesian, because Sherlock Holmes is, once you've removed everything that's not possible, then all that's left is what is possible. Yeah, or I mangled it, but that's the idea. Yeah.
Right. Yeah. So it's good to not be emotionally invested in one outcome, that this has to be true or this has to be false, but to actually actively work to prove both the one conclusion or its opposite. And sometimes you're surprised. Sometimes your initial guess is wrong, and actually the answer is the opposite of what you thought it is.
It sounds like at some point you're not doing math. You're just seeing if the universe respects effort. Right?
Yeah.
Come on, man, give it to me. I'm trying so hard here.
I'll throw you a bone on this one.
Come on. I got a headache. I'm supposed to take my wife to the ballet. I'm not going.
Yeah. You can sometimes feel that these problems have agency and sometimes some malice in some cases.
Malice.
We have another one?
Yeah. Good. One more. Good
Joel.
one.
Hello, Dr. Tyson, Professor Tao. Joel here from Chambersburg, Pennsylvania. Will a new math system have to be invented the more we explore space? It seems as if there are a lot of places in the universe where our math simply just breaks down.
Wow. Okay. So let me give a lead in, and I want to
nice intersection.
Yeah. Let me tee him up here. So it's not where our math breaks down, which in fact it does, but you don't blame the math for that. The math is just a representation of the physical model that we have created for the universe, right? So I have a physical model, and I say I want to represent it using math. And then I do that, and I calculate with it, hey, I'm getting some good answers here. And like, as Einstein did, you get some good answers. And then you reach the center of a black hole, and you end up dividing by 0, and that's no. And so the math blows up. But I'm not blaming the math, because that was just the math I used to represent my idea, and I need to modify my idea. Right. Don't blame this gentleman here just because your equation of your idea failed.
No, I'd blame him.
So in the broader context, could there be simply missing mathematics? That in the same way, the non-Euclidean geometry, we're scratching our heads over dark matter, dark energy, singularities, and they're the limits of our physical theories. Is there a new kind of math that we're just waiting for you guys to invent that can help us out?
I believe so. The math we have has become extremely good at explaining most of the universe. As long as you're not at extremely very tiny scales and extremely high temperatures, or like a black hole, like the rest of the universe, the math checks out. We can make measurements of galaxies, a billion light years away, and and all the measurements line up with what our current cosmological models give. The math works, but there are some the early universe and the center black holes. The current math is not giving us answers that make sense. In physics, I think that the biggest problem is that we don't have a theory of quantum gravity, which is the theory that would govern extremely strong gravitational fields at extremely small scales. I think the current theory is that we have to abandon our notions of space and time. Even non-Euclidean geometry will not be enough to understand what quantum space-time looks like. And there have been proposals. String theory is the most famous, but nothing has really stuck as being convincingly the answer.
One of your own people was right in the middle of this, Ed Witten, right? He's a mathematician who lent his efforts to string theorists.
Yeah, he's had a lot of ideas. Unfortunately, there was some string theory has very pretty math, but it doesn't seem to be fitting reality as much as the string theorists had hoped. So sometimes, even if the math is pretty, it's not the right answer.
So we get time for one more question.
One more question. This is a good one. This is Hayden from Hawaii. Like Dr. Tyson, my favorite movie is The Matrix. Is there a mathematical way to prove or disprove we are not in a simulation? Is anyone working on this? Now, if you answer no, that's exactly what the simulation would want you to say, which means we're in a simulation. Aha! I got you. Come on.
Yeah, you got to help us out. It's because a lot of people have existential angst over that question.
Right. It's a great question. We may not have enough. The bottleneck is not math. So there is a science, like if there's competing hypotheses explaining the world. So you're in a simulation, or the universe was created by a deity or whatever. There's a branch of statistics called Bayesian probability, which can help you guide which of these outcomes is more possible. You have to lay out all the possible scenarios that could be true, assign some prior probability to each being true, and then take all the data that you have, and there's a formula that allows you to take for every observation that you have, update. So some data confirms some theories and makes their probability go up, and some data makes some theories less likely and their probability goes down. And in principle, if you could compute everything, you could end up with and say, I'm 20% confident I'm in simulation, or 80% that the universe is real, or whatever. But the problem is that we don't know all the possible different types of universes that could happen, and we don't know what their prior probabilities are. And there's just so many of them. We can't compute how many of them would replicate a world that looks like ours. So while people attempt to do these calculations, there's just so many gaps, and there's a lot of implicit biases in how you choose which universes. Maybe some hypotheses you have implicitly set up to fail, or some that you're biased to make succeed.
You can't do it, because if you're trying to prove that that it's fake, the proof that you have is fake. So you're caught in this loop. So you have about
why would the proof be fake?
Because you're within a simulation that's fake. So the proof within the simulation is fake, right? Isn't that the argument? I mean, it's got the same credibility as as an email from a Nigerian prince at this point, right?
That's very dated.
Thank
That's like
you.
from 10 years
ago. How about
ago.
Amazon support? Yeah. How about that?
Yeah, you're still getting Nigerian prince emails? I
am.
That was like from 1994.
He doesn't have any friends.
Like two years after email.
If this were fake, the proof would be fake, which means that reality is not reality. So we don't even know if we're in reality.
Right. So you could never rule out a hypothesis with 100% certainty, because whatever data you have collected could itself be faked, as you said. But it just may take enormous effort. Like if you collect more and more data and it keeps pointing to a different hypothesis that the universe is real, whoever's doing the simulation will have to keep faking more and more data to consistently lead to a completely different outcome. And at some point, it's just, why would they go through so much effort?
So there's another pathway into this, which is when you program a world, there's a part of the program where you set up the basic parameters for it. How big is it? How old is it? What's the passage of time, population? You just set it up and you take it from there. Well, in our world, we can measure, for example, the energy of cosmic rays. Just take that as a thing. They get very, very high energies. You can imagine, suppose the energy distribution has an abrupt cutoff for no obvious reason. maybe that's the programmer's limit because they didn't think we'd ever get there. It's like the Truman Show.
Oh,
He's not going to
yes.
get to the edge.
Yeah.
So let's just you get to the edge and oh my gosh,
We didn't think
this
you
is
could
the edges of the programmer's parameters.
So you see the flaw in the program, and then you know you're in a
Or
program.
the limits of the program.
The limits of the program.
What do you think of that possibility? Because you can't program infinity, right?
Yeah, so it seems like if the universe was a simulation, whoever designed it has great attention to detail.
Yes.
At really fine scales or something, you still see the same laws of physics that you see. It's not like a cheaply made movie where once you're out of shot or something, everything's all made of cardboard. It wasn't made by a lazy simulator. It was made by a very obsessive simulator, if there was.
This is the first time I've ever heard the simulator complimented.
There you go. Well, maybe we are in a simulate. Maybe you are in a program. I mean, I'm getting endless spam calls about a loan that I supposedly asked about and took out or whatever.
That's a parallel universe where the Paul Mecurio in that universe
my God,
owes money.
It's 3 times a day. I'm telling you, we're in a simulation controlled by the banks.
The world is feeling less real these days, I think, just because there's so much simulated everything, unfortunately.
Yes, it is.
True.
And thank you, and good luck. I think sometimes you need a little bit of that as you explore that moving frontier.
Thank you. Yeah.
And Paul, always good to have you,
Good
man.
to have you.
Is your show still on the road?
Permission to Speak. Yeah,
Permission
my
to
Broadway
Speak.
show directed by Frank Oz. We're touring with that. I'm doing my podcast, Inside Out, with Paul Mecurio.
And I love that. And Permission to Speak, you engage the audience.
I
right?
do. I basically...
Which is a very important bit of improv.
Yeah. So we basically found that, everybody's got a story, and we're in a world where people want and need to tell their stories, and people share. And at
And
the
now
end
you
of the
can
show,
add some math to your...
yeah, I would love to have Terry come on stage. Ladies and gentlemen, welcome the T-Man.
As I said, anything's possible in this simulation. Yeah, so.
There you go.
That's the right answer
There
to
you go.
everything.
Great.
All right. This has been StarTalk, Cosmic Queries edition on mathematics of all things. Until next time, Neil deGrasse Tyson bidding you to keep looking up.